Gehry's design called for delicate, complex, curved walls, and the Guggenheim Foundation wanted huge exhibition spaces. To achieve both, the walls had to be thin. But this created the first problem.
The structural engineers faced the problem of ensuring the building was strong enough to support itself.
Concrete would have worked, but the walls would have been too thick. So the engineers decided to use a thin steel skeleton. But how could they be sure that the delicate framework would be strong enough to support the entire building?
The answer is in the shape. An example, if I just hold this piece of paper out, now, clearly it's not very stiff and strong at all, but if I change its shape, put a curve in it, suddenly it's a lot stiffer and a lot stronger.
So, changing the shape of a material by adding a curve makes it stronger. And just like this art, the Guggenheim is all curves, which led to a surprising suggestion.
The engineers quickly realized that they could turn the curved walls to their advantage by making them support the building and, in the process, create huge open gallery spaces. In fact, the engineers asked Gehry to make the curves even more pronounced, even more curvy. It's not often that an architect is asked to be even more outlandish by the engineers. The secret of the Guggenheim strength comes from an egg and a very special dam. Eggshell is famously fragile stuff. I mean, look, it just crumbles. But, as it turns out, chickens are perhaps better engineers than we've ever given them credit, because if you form eggshell into the right shape, it's capable of withstanding some pretty amazing forces, as I shall now demonstrate with this experiment.
Between these two sheets of plastic, there are 384 eggs glued in place with silicone.
These eggs are not hard-boiled, they're just as the chicken provided them. All we need now is a weight, something heavy. This will be perfect. Weighs about 3/4 of a ton, maybe. Only problem is it needs to be a bit more manageable. But that's okay, a few modifications, we can achieve that. Take it away. Quite rugged and rigorous modifications, but they'll do the job.
I'm not just crushing the car for fun, although it is fun. The car is going to be the load for my experiment. By compacting it, I'm distributing the weight more evenly.
Modifying cars, very fashionable with young people. Yep, there you go, modified.
Here to get things cracking is a man who knows all about curves, structural engineer Dr. Amer Waddy.
Yeah, you probably guessed we're going to put the car on the eggs. Well, that's the theory, Amer.
Yep.
How much difference can a shape make? I mean, how can an egg support a car?
Well, they are weak in one direction. Let's say if we loaded it like this on my index finger and my thumb, then we have one principal direction with a very, very weak curvature, which is almost flat, so it's almost a single curve. If we load it, however, on this way with the crown, then we have a very strong double curvature of equal amount in that direction.
To support the car, the weight has to be transmitted around the eggshell to the ground. The double curve allows the forces to flow evenly around a symmetrical shape. When the egg's on its side, the forces have to travel on a less direct path and around a shape that's not symmetrical, so the forces flow unevenly. This makes the egg weaker. The deeper the curve, the more vertical and so more direct the path is to the base, making it strong.
So it's those curves that give it the strength.
Yes.
And here, this is rather like when I curve that piece of paper, and suddenly it becomes much stronger, much stiffer because of the shape.
Yes.
And this then is a double curve.
Yes.
So, well, simply speaking, you've got twice the effect.
It's got twice the effect. In this case, you've only got the increase in strength in one direction. Here, you've got an increase in two directions.
And it's not just eggs that have curves in all the right places. In 1902, the egg's shape inspired an American engineer, Gardner Stewart Williams, to build the world's first double-curved dam.
Usually dams are built a bit like this. Well, not exactly like this, it's not a dam, it's an art installation. But the point is, traditionally dams are narrower at the top, growing bigger and wider towards the bottom, using sheer size and bulk to hold back the weight of a man-made lake.
Concrete dams often have one curve, like arches, but tipped on their side. As the water presses against the curve, the pressure is spread along it. The combination of sheer size and the arch shape holds back the water, but it takes a lot of concrete to build. Still, for strength, one curve is good, but two curves are better. Williams realized this when he designed a radical new type of dam in Ithaca, New York State. His new cupola dam needed far less material because making it double curved meant it could be much thinner, but just as strong. Williams designed his dam to be 27 meters high and just 2.5 meters thick. That's less than half the thickness of a traditional arch dam of that height. Very thin indeed.
So narrow, in fact, that locals were so worried it might burst, they insisted construction was halted at a third of its planned height.
Although it only reached 9 meters high, Williams's dam still holds back water in Ithaca. And his double-curved idea continues to be used in dams today. But just how strong is a double curve? Is it enough for these eggs to take the weight of an entire car?
Are you happy it's lined up?
A modification.
I've already modified the car. It's important, that's why we've got to adjust the whole thing now, that the car is lowered down flat onto the eggs, because obviously if it goes down one side or the other first, then all the weight will be focused on just a few eggs. We need to spread it amongst all of us. See, there's more science to this than you'd think. It's a precise thing.
Good lad, though. There we go.
This is just eggs. They're not hard-boiled, as the chicken provided them. Away we go. This could get messy if it doesn't work.
It could. And we're right in the firing line.
Yeah, well, you worked it out. You said you could do it.
3/4 of a ton of car versus some eggshell.
It's so messy.
Oh, I can hear some...
I can
hear cracking.
Is that it?
I think it's worked.
I always said it would. I always said it would.
There are only chicken eggs holding up a whole car.
Now, in actual fact, you worked it out. You reckon that those eggs could hold more than that?
I think so, yeah.
What I'm getting at is I've got another crushed car.
The eggs are supporting 3/4 of a ton already, but could the double-curved shape let them hold more? Can they take a second car?
This is going to be the fun part.
You'll hear them say things like left a bit, right a bit. Precision.
Yeah. Oh, I can hear cracking again.
I can hear cracking.
Some rather intriguing cracks I can hear now.
These eggs have delivered. I mean, they really have. That's 2 cars. I think we've proved the point.
Thanks to their double curve, these eggs are supporting over 1.5 tons.
One final thing, just in case you thought, yeah, hang on, they're all hard-boiled eggs or made out of concrete, I'd just like to prove they are all real, raw eggs. Amy, are you ready?
Yep.
OK, line up your wire.
Uh-huh.
A bit closer, a bit closer, a bit closer. Are you happy?
Yep.
OK, right, let's go. 1, 2, 3, go! Yep. Definitely real eggs. Stronger than you think, and all thanks to that shape, the double curve. And like dams, eggs, and boats, the walls here at the Guggenheim are built with a double curve to give them their strength.